All right, so natural logs and exponentials. We've kind of already seen this stuff a little bit, some easier problems. Problems where you're sort of just doing the straightforward version of these integrations. So let's take a look at some trickier ones to spot. So starting off, this is kind of a trick, and I'm not saying it's a great trick that's always true, but when you're looking for your u, and you have one of these big fractions, and you're looking for your u, it's probably either the numerator or the denominator. And if it's just polynomials and stuff, it's probably the denominator. So let's take a crack at setting u equal to x squared plus 2x minus 7. So our du then would be 2x plus 2. And sure enough, that's pretty close to what I've got upstairs. If I just multiply this by 2, and of course put the 1/2 out front to compensate, then I've got 2x plus 2 upstairs. So everything matches. So I could rewrite this problem as 1/2 the integral of 1 over u du. Alright, so if you integrate 1 over u, that's really just u to the negative 1. So we add 1 to the power and we get u to the 0 over 0 plus c. Oh wait, no we don't, do we? Because, I mean, I've reminded you a few times now, and I'll probably do it again in the future. Anytime you see u to 0 over 0 or something to the 0 over 0, this should just be your tip off, hey, that doesn't exist. And that is correct. This is the exception where it's natural log. So if you have u to the minus 1, or 1 over u, that's the natural log integral. So this is actually 1/2 ln of u plus c. And then, of course, we just plug in our u, which is x squared plus 2x minus 7. Got to keep you on your toes by doing things wrong every once in a while. All right, not too bad. Pretty straightforward. So let's take a look at what happens when natural logs are weird. So first of all, we've got a natural log in this thing, and even though we know the integral of 1 over x is natural log, what's the integral of natural log? I don't know. You probably don't either. So this is actually a power rule in disguise. But the weird thing is, when you see this x downstairs, this actually immediately breaks the rule I gave you a second ago, which is look downstairs for your u. That's actually not quite as accurate as the number 1 rule, which is true in this case. If there's parentheses and a power, that's probably your u is what's in parentheses. So in this case, the natural log is actually our u. So u just equals ln of x. Not just x, the whole ln of x, because that's what's being raised to a power. And then this x downstairs, you'll see, is actually part of our du. Because the derivative of ln of x is 1 over x. And that explains where this x comes from. You could rewrite this as integral of natural log of x squared, and then just sort of take that x out of the denominator and make it like this. Just make it a 1 over x fraction to make it more obvious that this is just your du. And of course, this is our u squared, so we're really integrating u squared du. Alright, so at that point it becomes pretty straightforward. U cubed over 3 plus c. And of course that means we got to plug in our u again, so ln of x cubed over 3 plus c. Alright, so that one wasn't too bad. You know, once you realize your natural log is your u, that explains what the x is doing here. But check this out. What's up with this one? Once again, I got a natural log, which should make me nervous because I don't like to integrate natural logs because it's very hard to do if it can be done. But I've got, again, a mysterious x plus 5 downstairs. So this is actually a really well hidden power rule because there's no exponents at all, and yet we're going to integrate it as a power rule. Because when you're looking at this problem, what you should be thinking is, I'm kind of hosed here. So if I make x plus 5 my u, then I'm trying to integrate, and I do my substitution with u equals x plus 5. Then if you rewrite this in u's, you'd be like ln of u over u. But that doesn't work, because if your u is x plus 5, this isn't quite right. The integral of 1 over u would be natural log, but integral natural log over u, this just doesn't work. So it turns out the big trick here is to think of this as the natural log of x plus 5 to the first power. Because you can always put a 1 exponent on anything you want. So that means our u is going to actually be ln of x plus 5, which means our du is 1 over x plus 5 dx. So the same thing happens as in the previous problem. Just because there's no exponent doesn't mean we can't use the power rule. So I'll rewrite this as integral of u to the first power times du. Because this right here, this 1 over x plus 5 dx, is really just our du. And integrate u to the first power, you just get u squared over 2 plus c, which equals the natural log of x plus 5 squared over 2 plus c. Alright, so pretty wacky, but hey, that's a well-hidden power rule right there. And that could happen with trig functions also, where you end up treating a tangent or something to the first power and integrating it and getting the tangent squared because the du's match up. Alright, exponentials, not too bad. This top one is really straightforward. It's just e to the u. So u equals 3x, du equals 3 dx, which means I need a 3 here, and then 1/3 out front. So just get integral of, so 1/3 integral of e to the u, and that's basically just exactly our integration formula. Integral of e to the u is just e to the u plus c. Of course, we got to keep our 1/3. So we end up with 1/3 e to the 3x plus c. All right, what's up with this one? Very similar. X out front might seem a little disconcerting, but if you look at this and you're like, well, it's probably an exponential. Maybe that x is part of my du. So we'll try setting u equal to x squared minus 3, since with exponentials, the exponent is your u. So du would equal 2x dx. And sure enough, that means I needed this x out front. So put a 2 there, 1/2. So now I've got my du is the 2x times dx, which means I'm just integrating 1/2 of u, I'm sorry, e to the u, du. So that's 1/2 e to the u plus c, and therefore I've got 1/2 times e the x squared minus 3 plus c. Not too shabby. Exponentials are really pretty easy to spot most of the time. If there's an e in there, there's a good chance you're using your exponential formula. Alright, so what's up with this one? Well, let's find out. See a 2x plus 1 in parentheses, and I got this. If you've done integration by parts, which would be actually after this class quite a bit, but you might be thinking maybe I use integration by parts on this, but hey, when in doubt, this might be a harder problem, but there's a decent chance it's just your usual e to the u problem. So let's just pretend for a second that u is just the exponent like it usually is with e problems, and set it equal to that. So that would mean our du was 2x plus 1 times dx. Oh, and sure enough, we just happen to have a 2x plus 1 and a dx, right? So, yep, that means it's just your usual e to the u du problem. So that's just going to equal e to the u plus c. And at this point, we get rid of our u, put back in our x squared junk. So we get e to the x squared plus x plus 5 plus c. All right, this bottom one, you might be thinking the same thing would happen, except the problem is it's not quite that simple. We got some irregularities here. If you made this your u, then your du would have an e to the x minus 3 in it, not an e to the 2x. And of course, if you made this your u, that wouldn't work either. Or if you made the 2x your u, derivative of 2x is not e to the x minus 3. So nothing matches up here. If you're sitting there trying to find your u's and your du's, turns out this is actually an algebra problem. What we need to do is just distribute in, just multiply this out essentially. Because when you multiply e to the 2x times e to the x minus 3, they have the same base. So that's going to just end up being e to the 2x plus x minus 3. We're just combining the exponents by adding them. And then of course there's a dx. I'm just going to split this into two integrals because they're going to have different u's. And then we got 4e 2x dx. Alright, so the reason I had to split these into two integrals is I have two different u's. In this one, my exponent, I should combine all those like terms first. So my exponent becomes 2x plus 3x plus x is 3x minus 3. And 4e to the 2x dx. So you can see the reason I split these into two separate integrals is that's kind of how you do integrals anyway. If you have terms added together, you're going to integrate them one at a time. But then also, these have different u's. So I want to use my e to the u integration formula for both these problems. But in this one, u equals 3x minus 3. And in this one, u equals 2x, because they have different exponents of e. So my du over here equals 3 dx. And my du over here equals 2 dx. Which needs I did 2 there, and therefore 1/2 out front. And on this one I need a 3 dx, so that means I need a 3 there, and therefore 1/3 out front. Alright, so that integrates to 1/3. Now you can see how u sub would be kind of, if I do all the u junk, it's going to be tricky. So this time I'm just going to realize, you know what? I've already got my du's matched up. Therefore the integral of e to the 3x minus 3 is just e to the 3x minus 3. And the integral of 1/2 of e to the 2x is just e to the 2x. But of course I got a 1/2 times a 4, so that's 2 e to the 2x and plus c. So sometimes when you have two different integrals in the same problem, they both have u's. It can get confusing which u is which and all that, so avoid if you can. Rational exponents. Not sure why. Oh, rational exponentials. That makes more sense. Got exponentials divided by exponentials. Couldn't figure out what my own title meant. Alright, so what's going on here? This is actually surprisingly going to obey the first rule I told you, which is that when you're looking for a du, look to the denominator. And that's just because, looking at this, it's not obvious what could possibly be going on. We have a power downstairs, and that gives me a strong suspicion I want to use the power rule. But if you pick anything else for your du, it's just not going to work out. So let's make our u equal. Doesn't make a lot of sense, right? This isn't normal, but let's make our u whatever the power is of. So e to 2x plus 4, which means our du is the 4 goes away, and we just get derivative of e to the 2x is 2e to 2x. That 2 right here came from the chain rule. So when you take the chain rule derivative of an exponential, you gotta multiply by u prime, and your u prime would be derivative of 2x. Alright, so that means I need a 2 upstairs, and therefore 1/2 right here. But now you can see I've got my du's matched. So this is now integrating 1/2 u to the minus 3 du. So that's going to be 1/2 u to the minus 2, because we just add 1 to the exponent, and then we divide by the new exponent. Makes sense, yeah. Plus c. Alright, so that means we get negative 1/4. And then u to the negative 2 is really just u squared downstairs. So e to the 2x plus 4 squared plus c. Alright, last one we're going to do of these rational exponentials. Let's see. So once again, it looks like I've got a situation where it's not obvious what u would be, and I can't just split this up because I have 2 terms in the denominator, so there's no algebra I can really do here. But I could look at this and say, when in doubt, the denominator might be your u. So let's just pretend for a second that u equals 1 minus e to the 3x. That would mean my du would just be negative 3 e to 3x. Again, we've got a chain rule situation where the derivative of the exponent ends up being a coefficient right here. And sure enough, I actually have an e to the 3x to work with. I just need a negative 3 right here. And of course, to compensate, that means I need a negative 1/3 out front, because these two coefficients have to multiply out to be 1. Otherwise, I cheated the gods of algebra. So at this point, I got negative 1/3 times the integral of my upstairs is just du, and downstairs I've got u. And now I won't go through the drill of putting e to the 0, u to the 0 over 0, because I think we're all aware now that this is negative 1/3 ln of u, which equals negative 1/3 ln of 1 minus e to 3x plus c. All right, there you go. So when in doubt, trying to figure out what your u might be, what your du might be, you just gotta pick one and go for it and see if your du matches up, as it obviously did in these. All right, so last ones we'll do right now, non-e exponentials. All we mean by that is this is still an exponential. So if you look at this formula over here, and of course we could replace everything here with u's. So that's a u, du, a to the u. But the point is that a is a number besides e. And this would work for e too. If you wanted to use this formula using e, you would just get the same thing we always get. Because if you have an e in here for a, then downstairs on the right you would just have an ln of e, which is just 1. So really the e formula is just a special case of this. But the moral of the story is, if you have a number other than e being raised to a u, then you've got to put the natural log of that base in the denominator on the right. So it's just plug and chug. I just want to make you aware of the kind of what we're doing is compensating. I always think of this natural log downstairs as sort of like making up for the fact that we're not using e. It's like, sorry integration, we're not using e, but hey, I'll make it up to you. I'll put a natural log of the base downstairs. Only someone in calculus could think of it that way, but hey. Any dumb thing you can think of to help you remember something, no matter how dumb it is, if it helps you remember it, it's worth doing. All right, so 3 to the 5x, if our u is just the exponent, because that's how this formula looks, du is 5dx, so I just do the usual, put a 5 there, which means I need a 1/5 out front to make up for it. And now I just plug and chug through the formula. So I keep my 1/5 out front. Then I need a to the u, so basically the same exponential I started the day with. But then I've got to divide by the natural log of the base, so natural log of 3. So I end up with 3 to the 5x over 5 ln of 3 plus c. Yep. All right, next one. So this, I designed this one obviously to look really crazy. Maybe wondering, whoa, what's pi doing there? But pi is just a number. It's just 3.14. And e is actually just a number as well. E is just 2.7 something. If you ever want to know what e is, by the way, you can just do, if you look on your calculator, the natural log button, if you look up above it in really small writing, there's e to the x. So that allows you to take the exponent of e. There's raise e to an exponent, to a power. So if you just hit second and then ln e, get that e to the power and just put in a 1 and hit enter, you'll get e to the 1, which is 2 to the 1, whatever. So if I do that, I get 2.718281828. I don't think it repeats. It's just a non-repeating, never-ending decimal. But the point is, pi is just a number, which means we can use this a to the u formula, which I know you're all very excited about. So really my u is just sine x, the exponent, which means my du is cosine of x dx. Oh, look at that. I've got it right there. So that explains why we've got such a mess. It's because this was all part of the du. And finally, we could just make a note that, hey, a equals pi. So when we're plugging into the formula, we'll know exactly what to plug in. So this is simply going to be a to the u. So pi to the u. So basically the same thing we started with, divided by the ln of a, which is pi, plus c. Pretty crazy. Now you might be thinking, hey, we could cancel these pi's out. But you can't because of the natural log of pi. Just think of this as like a unit that can't be separated. And then pi up here is just a coefficient. So we're kind of hosed. This is the best we can do. All right, so that's logs and exponentials. Hopefully I've shown you some of the tricks and the ways that they can sort of disguise these problems. But really what it comes down to when you're doing integrals is it's just going to get harder and harder to spot the rule. So if you have not too bad a class, like you're in calculus for business or something, then you might not get into super nasty problems. But especially if you're an AP and have kind of a hard teacher, then the concepts aren't that bad. You'll just be using the same formula like power rule again and again. But it can become harder and harder. They can do harder and harder problems. They make it trickier and trickier to spot what is the u, what is the du. And I hope I showed you in this video that that 1 over x can frequently be the big trick, the powers of log.